When dealing with a 480-volt, 3-phase, 400-amp electrical service, there are specific requirements regarding disconnects and grounding. Let's clarify the questions about the power company's POCO unfused disconnect and the need for separate ground and neutral conductors. The unfused disconnect on the POCO side is generally not considered the first disconnect for the building's electrical system. The primary disconnect is the one that's accessible to the building owner or occupant, typically located within the building or immediately outside. Therefore, in your scenario, the 400-amp fuse disconnect would be considered the first disconnect from the perspective of the building's electrical system. Regarding the separation of ground and neutral conductors at the 400-amp fuse disconnect, the answer is yes, separate ground and neutral conductors are required. This requirement is based on the 2020 National Electrical Code (NEC) and subsequent editions, which mandate a separate equipment grounding conductor (EGC) and a neutral conductor for new electrical services. The purpose of the equipment grounding conductor (EGC) is to provide a low impedance path for fault currents to return to the source. This low impedance path facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses, thus minimizing the risk of electrical shock and fire hazards. The neutral conductor provides a return path for the normal flow of current in the electrical system. Separating the ground and neutral conductors ensures that fault currents flow through the equipment grounding conductor (EGC) and not through the neutral conductor. This separation is crucial for safety and proper system operation. To elaborate further, consider these key aspects of grounding and bonding. Firstly, the grounding electrode system. This system connects the electrical system to the earth. It typically includes grounding electrodes such as ground rods, ground rings, or metal water pipes that are in direct contact with the earth for at least 10 feet. The grounding electrode system provides a reference point for the electrical system and helps to stabilize voltage with respect to ground. Secondly, the equipment grounding conductor (EGC). This conductor provides a low impedance path for fault currents to return to the source, as previously mentioned. It connects the non-current carrying metal parts of electrical equipment, such as enclosures and conduit, to the grounding electrode system. Thirdly, bonding jumpers. These jumpers are used to connect different metal parts of the electrical system to ensure that they are at the same electrical potential. Bonding jumpers are commonly used to bond metal conduits, enclosures, and other metal components to the equipment grounding conductor (EGC). The NEC provides detailed requirements for grounding and bonding in Article 250. It covers various aspects, including the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal parts. It is crucial to adhere to these requirements to ensure a safe and effective grounding system. Now let's discuss the location and function of the POCO's unfused disconnect. The unfused disconnect on the POCO side is usually installed by the utility company. Its primary function is to allow the utility to disconnect the electrical service from the meter for maintenance, repairs, or in case of emergencies. This disconnect is typically located before the meter and is not intended to provide overcurrent protection. The 400-amp fuse disconnect, on the other hand, is installed by the building owner or contractor. Its purpose is to protect the building's electrical system from overcurrents such as short circuits and overloads. The fuses in the disconnect are sized to protect the conductors and the equipment downstream from the disconnect. Proper installation of the separate ground and neutral conductors is essential. These conductors are typically installed in a conduit or cable. The equipment grounding conductor (EGC) should be green or green with a yellow stripe to clearly identify it. The neutral conductor is typically white or grey. When running the conductors, it is important to avoid ground loops, which can occur when there are multiple paths for current to flow to ground. Ground loops can cause unwanted current flow, which can interfere with the operation of electrical equipment and create safety hazards. To prevent ground loops, it is important to ensure that there is only one connection between the neutral conductor and the grounding system. This connection is typically made at the service entrance. Complying with all applicable electrical codes and standards is paramount when installing an electrical service. The NEC provides comprehensive guidelines for electrical installations covering various aspects such as wiring methods, overcurrent protection, grounding, and bonding. Local codes may also have additional requirements that must be followed. It is crucial to consult with a qualified electrician or electrical engineer to ensure that the electrical installation meets all applicable codes and standards. Let's delve deeper into some specific NEC requirements related to grounding and bonding, focusing on areas relevant to your 480-volt, three-phase system. NEC Section 250.24 addresses grounding of service-supplied alternating current systems. It requires that the neutral conductor be grounded at the service entrance. This connection is typically made to a grounding electrode system which, as mentioned earlier, includes items like ground rods, ground rings, or metal water pipes. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. It is important to select the correct size grounding electrode conductor to ensure that it can safely carry fault currents. NEC Section 250.28 covers bonding jumpers. Bonding jumpers are used to connect different metal parts of the electrical system to ensure that they are at the same electrical potential. This helps to minimize the risk of electrical shock and fire hazards. Bonding jumpers are commonly used to bond metal conduits, enclosures, and other metal components to the equipment grounding conductor EGC. The size of bonding jumpers is determined by NEC Table 250.102 cone based on the size of the service entrance conductors. It is important to select the correct size bonding jumpers to ensure that they can safely carry fault currents. NEC Section 250.122 specifies the size of equipment grounding conductors EGC. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit. NEC Table 250.122 provides guidance on selecting the appropriate size EGC. For example, if the overcurrent protective device is rated at 400 amps, the EGC must be at least number 3 AWG copper or number 1 AWG aluminum. It is important to select the correct size EGC to ensure that it can safely carry fault currents and provide a low impedance path for fault currents to return to the source. NEC Section 310.16 provides ampacity tables for conductors. These tables specify the maximum current that a conductor can carry safely based on its size, installation type, and installation conditions. It is important to select conductors with sufficient ampacity to carry the expected load current. When selecting conductors, it is also important to consider dirting factors, which may be required based on the number of conductors in a raceway or cable, the ambient temperature, and other factors. NEC Section 408.41 addresses the separation of neutral and equipment grounding conductors in panel boards. It requires that the neutral and equipment grounding conductors be kept separate in panel boards except for the service panel board, where the neutral conductor is bonded to the enclosure. This separation helps to prevent neutral current from flowing through the equipment grounding conductor EGC, which can cause unwanted voltage drops and create safety hazards. In summary, when working with a 480-volt, three-phase, 400 amp electrical service, it is crucial to understand the requirements for disconnects, grounding, and bonding. The POCO's unfused disconnect is typically not considered the first disconnect for the building's electrical system. Separate ground and neutral conductors are required at the 400 amp fused disconnect, in accordance with the NEC. Proper installation of the grounding and bonding system is essential for safety and proper system operation. Consulting with a qualified electrician or electrical engineer is highly recommended to ensure that the electrical installation meets all applicable codes and standards. Let's further discuss the practical implications of these requirements. When installing the 400 amp fused disconnect, it's crucial to ensure that the enclosure is properly bonded to the equipment grounding conductor EGC. This bonding provides a low impedance path for fault currents to return to the source, which helps to quickly trip the overcurrent protective device and minimize the risk of electrical shock. The bonding can be achieved by using a bonding jumper to connect the enclosure to the EGC. The size of the bonding jumper should be selected based on NEC Table 250.102 current. When running the separate ground and neutral conductors, it's important to maintain the separation between them. The equipment grounding conductor EGC should be run with the circuit conductors in the same raceway or cable. This helps to minimize the impedance of the grounding path and ensure that fault currents can quickly return to the source. The neutral conductor should be insulated and should not be used as an equipment grounding conductor EGC. When terminating the conductors at the disconnect and panel board, it's important to use the correct connectors and terminals. The connectors and terminals should be listed for the type of conductor being used and should be properly tightened to ensure good electrical connection. Loose connections can cause overheating and arcing, which can create safety hazards. It's also important to label the conductors properly. The equipment grounding conductor EGC should be labeled with green tape or green paint. The neutral conductor should be labeled with white tape or white paint. Proper labeling helps to ensure that the conductors are correctly identified and connected. When selecting the fuses for the 400 amp fuse disconnect, it's important to choose fuses that are rated for the voltage and current of the circuit. The fuses should also be sized to protect the conductors and equipment downstream from the disconnect. The fuse manufacturer's recommendations should be followed when selecting the appropriate fuse size. It's important to note that the NEC requires that all overcurrent protective devices be readily accessible. This means that the disconnect and panel board should be located in a place where they can be easily reached for maintenance and repairs. The disconnect and panel board should also be protected from physical damage. In addition to the NEC requirements, there may be local codes and regulations that must be followed. It's important to check with the local authorities to determine if there are any additional requirements. Following all applicable codes and standards is essential to ensure a safe and reliable electrical installation. It's also important to perform regular maintenance on the electrical system to ensure that it is operating properly. This maintenance should include inspecting the conductors, connectors, terminals, and overcurrent protective devices. Any damaged or worn components should be replaced immediately. Regular maintenance can help to prevent electrical problems and ensure the safety of the electrical system. When troubleshooting electrical problems, it's important to follow safe work practices. Always to energize the circuit before working on it. Use a properly rated voltage tester to verify that the circuit is de-energized. Wear appropriate personal protective equipment PPE such as gloves and safety glasses. If you are not qualified to perform electrical work, it's best to call a qualified electrician. Working on electrical systems can be dangerous, and it's important to take the necessary precautions to protect yourself from electrical shock and other hazards. Let's address some common misconceptions about grounding and bonding. One common misconception is that grounding is only for safety. While grounding is certainly important for safety, it also plays a role in the proper operation of electrical equipment. Grounding helps to stabilize voltage and reduce electrical noise, which can improve the performance of sensitive electronic equipment. Another common misconception is that the neutral conductor and the equipment grounding conductor EGC are the same thing. While the neutral conductor and the EGC are both connected to ground at the service entrance, they serve different purposes. The neutral conductor provides a return path for the normal flow of current, while the EGC provides a low impedance path for fault current. A third common misconception is that all metal parts of the electrical system must be grounded. While it's important to ground all non-current carrying metal parts that are likely to become energized, it's not necessary to ground every single metal part. The NEC provides guidance on which metal parts must be grounded. It's important to understand these common misconceptions and to ensure that the electrical system is properly grounded and bonded. Proper grounding and bonding are essential for safety, reliability, and performance. To further clarify the grounding requirements, consider a scenario where a fault occurs in the electrical system. For example, imagine that a wire inside an electrical enclosure comes loose and touches the metal enclosure. If the enclosure is properly grounded, the fault current will flow through the equipment grounding conductor EGC back to the source. This high fault current will quickly trip the overcurrent protective device, such as a circuit breaker or fuse, which will de-energize the circuit and prevent the enclosure from becoming energized. However, if the enclosure is not properly grounded, the fault current will not have a low impedance path back to the source. This can cause the enclosure to become energized, which can create a shock hazard for anyone who touches it. The amount of voltage that the enclosure reaches depends on the available fault current and the impedance of the fault path. In some cases, the voltage can be high enough to cause serious injury or even death. Proper grounding is essential to prevent these types of hazards. It provides a low impedance path for fault currents, which helps to quickly trip the overcurrent protective device and minimize the risk of electrical shock. In addition to safety, grounding also plays a role in the proper operation of electrical equipment. Grounding helps to stabilize voltage and reduce electrical noise, which can improve the performance of sensitive electronic equipment. For example, computers and other electronic devices can be affected by voltage fluctuations and electrical noise. Proper grounding can help to minimize these effects and ensure that the equipment operates reliably. Grounding is also important for lightning protection. Lightning strikes can cause severe damage to electrical systems and equipment. A properly installed grounding system can help to divert lightning currents to ground, which can reduce the risk of damage. It's important to note that grounding is not a substitute for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. Grounding provides an additional layer of protection by providing a low impedance path for fault currents. Both grounding and overcurrent protection are essential for a safe and reliable electrical system. Let's consider the specific requirements for your 480-volt, 3-phase, 400-amp electrical service. The NEC provides detailed guidance on the grounding and bonding requirements for this type of service. It's important to consult the NEC and to follow all applicable codes and standards. In addition to the NEC, there may be local codes and regulations that must be followed. It's important to check with the local authorities to determine if there are any additional requirements. Working with electricity can be dangerous, and it's important to take the necessary precautions to protect yourself from electrical shock and other hazards. Always energize the circuit before working on it. Use a properly rated voltage tester to verify that the circuit is de-energized. Wear appropriate personal protective equipment (PPE) such as gloves and safety glasses. If you are not qualified to perform electrical work, it's best to call a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. They can also ensure that the electrical system meets all applicable codes and standards. In conclusion, understanding the disconnect requirements between the POCO and the building owner, as well as the necessity for separate ground and neutral conductors, is vital for a safe and compliant electrical installation. Always refer to the latest edition of the NEC and local codes, and consult with qualified professionals for any electrical work.